Okay, let's look at some other questions from the study guide. So these three questions ask you to simplify the logarithm. And we need to know that these logarithms, the first two anyway, are log base 10. We usually don't write the base when we're dealing with log base 10. But if you remember, a logarithm is basically just an answer to the question, what do I have to, or what power do I have to raise the base to get the answer? So this log is really log base 10 of 10 let's see, log base 10 of 10 million. So this is thousands, 10,000s, 100,000s, millions, 10 millions. So I say you can either find this on the calculator, or it's really easy to realize that as a power of 10, 10 is, if I multiply 10 by itself 3 times, I'll get something that has 3 zeros. If I multiply 10 by itself 5 times, I'll have something that has 5 zeros. So really I can rewrite this as log base 10 of 10 to the 1, 2, 3, 4, 5, 6, 7. And so when I do that, another property of logarithms come into play here. And that property is, if I have a log that has the base the same as what I'm taking the log of, then I can just get rid of that and I just have x. So here, log base 10 of 10 to the 7th is just 7. So here, I can rewrite 1 over 100 as log base 10 of 1 over 10 squared. And then I can rewrite that as log base 10 of 10 to the negative 2, because if I take this 10 squared and move it up to the numerator, I have to change the sign of the exponent. So log 10 of negative 2. Or I'm sorry, log 10 of 10 raised to the negative second power. Log 10 of 10 cancels, and I'm just left here with negative 2. So remember that, I also want to tell you that if you have a logarithm that doesn't have a base, it's base 10, and we call that a common logarithm. So these two are common logarithms because they have a base 10. Now, a natural logarithm is a logarithm that has a base of e. So we have log base e, and e is sometimes called the natural number, not to be confused with natural numbers, or the natural base. Sometimes it's called the natural base. But when we have log base e, we can rewrite that as ln. People usually do. So if I have ln, that's really log base e. So this is really log base e of e to the 10th. Notice that log base e and e will cancel each other out, just like log base b and b does. And so here I'm left with 10. So 7, negative 2, and 10. Alright, number 6, we want to determine if each situation is an example of linear, exponential, or logistic growth. Remember that linear growth is constant. Exponential growth starts out small, but then grows more rapidly as we go over time. And also remember that logistic growth has a carrying capacity, or it will taper off. The growth will when the carrying capacity is approached. So let's see situation A. The number of goats in a certain mountainous area grows until the population reaches 250. Scientists who are studying the goats notice the population declining during the next 2 years. Alright, so the number of goats grows until the population reaches 250. Then it starts to decline. This is logistic growth. So that's logistic growth. Sorry about my writing. And in fact, 250 is the carrying capacity. So what about Robert gets a summer job each week. When he gets his paycheck, he places $20 in a jar. At the end of the summer, he plans to use the money to buy school supplies for the upcoming year. Alright, so summer job puts each week $20 in a jar. So each week you're putting the same amount. The growth is constant. This is linear. Alright, Sam won $25,000 when he appeared on the game show Wheel of Fortune. After paying the required taxes, he places the remaining money in the bank in a savings account and draws 5% interest annually. In 10 years, he plans to use the money to travel around the world. Well, we didn't actually say this in the beginning, but another characteristic of exponential growth is that it usually grows proportionally to the population that's present, or by some percent of the population that's present. So this has a percent in it, so it is in fact exponential growth. Alright, let's continue. This says a population of beetles is growing according to a linear model. The initial population at week 0 was 9. After 5 weeks, the population grew to 34. We want to find an explicit formula, P sub n, for the number of beetles after n weeks. We want to find out what the beetle population during week 3 was, and we want to determine if our estimation in part B is an instance of interpolation or extrapolation. Alright, so if I need to come up with an explicit formula, I need to have P sub n, and that's going to be P sub 0 plus the common difference times n. Alright, so I know P sub 0. P sub 0 is 9, right? So the initial population was 9. So P sub 0 is 9. Now I need to find the common difference. Well, let's think about this. How much do we know that the beetle population grew? Well, it grew from 9 to 34. So it grew by 25 beetles, right? So the population grew by 25 beetles. There were 9 beetles initially. After 5 weeks, there were 34, so we added 25 beetles on. How many weeks did it take us to add the beetles? 5 weeks. So if I take 34 divided, or minus 9, divided by 5, this is in 5 weeks we added 24 beetles. So how many beetles did we add per week? Well, 25 divided by 5, that's 5 beetles per week. That's the common difference. So our formula for P sub n will be 9 plus 5 n. Now, what was the beetle population during week 3? Well, we're just going to find P sub 3 here. So that's going to be 9 plus 5 times 3. So 5 times 3 is 15, and 15 plus 9 is 24, right? 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 24. So after 3 weeks, we have 24 beetles. Now, is this an instance of interpolation or extrapolation? Well, we know that the beetle population was growing for 5 weeks in a linear model. 3 weeks is less than 5, so this is within the information we know. So this is an instance of interpolation because we are, sorry about that, we're using what we, no, I mean, we know the trend has continued. If I wanted to say, what will the beetle population be after 20 weeks, I'd have to say if this trend continues, because you can't be sure that the linear trend or the growth by 5 beetles per week will continue after these 5 weeks. But since we've observed that over 5 weeks, we can be pretty sure that our estimation of the number of beetles at week 3 is pretty accurate. So this is an example of interpolation. All right? Excellent.